This is part 2 of my video series about our conservation of momentum formative. And we have three free response problems here. And I'll start by just walking through the first one. We've got a boy running at 2 meters per second. He jumps onto a skateboard, and I added something here. The skateboard is at rest. And so if I will edit my document to update it. It's good to be clear about that. The skateboard is not moving. And we're meant to calculate the final velocity of the boy and the skateboard. And so it's important to notice that well, I'm recording all of the stuff that's been given to me here in this problem. And I've chosen to use, remember, we use subscripts intentionally. So this is the mass of the boy and the mass of the skateboard. And so I'm using my subscripts to really indicate what objects I'm talking about. Also, what state I'm talking about. And so we know that the initial velocity of the boy is 2 meters per second, and the initial velocity of the skateboard is 0 meters per second. And then the thing that I'm looking for, it says the final velocity of the boy and the skateboard. And so we imagine that the two objects in this system, the boy and the skateboard, have the same final velocity, and that's what we're looking for. And they have the same final velocity because the boy is standing on the skateboard. So the basic formula here I've written is that the total initial momentum is equal to the total final momentum. This is a momentum conservation problem. What I did was I split my momentums here into the initial momentum of the boy and the initial momentum of the skateboard. Add those together, and that equals the final momentum of the boy plus the final momentum of the skateboard. And I've zeroed out my skateboard momentum initially because the skateboard is at rest. So when I expand using the definition of momentum, I just get here the momentum of the boy initially on the left, and then on the right-hand side, the momentum of the boy after he jumps on the skateboard, plus the momentum of the skateboard here. And notice that, remember, these two quantities are equal, so I'm going to factor this thing right here, and now I'm just left with the final velocity, just one thing that I'm looking for, and that's just the distributive property right there. So now I can solve this for that final velocity here, and again, it's just worth noticing once again, we do all of our work symbolically, so that afterwards, so that now that I have everything that I know on the right-hand side of this equation, and then the one thing that I don't know on the left that I'm looking for. When I plug everything in, I get a final velocity of 1.9 meters per second. Of course, I only have two significant digits in each of my inputs here, and all the things that are given to me. So I'm only including two in this. And I also noted the direction of this velocity in my solution. And it's good to think about it too. Look, this is a little bit slower than the boy was going at first, and that makes sense that there's more mass afterwards that's moving, so the speed is going to have to be slower. So good to check conceptually about our solution. Now, the next problem these are all conservation of momentum problems, really, just in one form or another. And again, I've used my subscripts intentionally. I've got a snowball and a person, M sub p. I'm just calling p for person. That in the text here, we're talking about an ice skater. And really, what are they doing? They're holding a snowball and gliding on the ice, and then he throws the snowball at his best friend with a certain speed, and we're looking for the final velocity of the ice skater after he throws the snowball. Again, I've got my conservation of momentum happening here. Initially, the snowball and the person are moving, and we sum up their momentum. And then after he throws the snowball, the momentum should be the same for these two objects. So again, expanding using the definition of momentum, and then solving for the velocity, the final velocity of the person here. And once again, get everything that you know on one side and the one thing you don't know on the other side. And then it's just a matter of plugging everything in and then observing the significant digits. Again, the velocity of the person is now 1.5 meters per second in the same direction as the person was going initially. And that all came out of the mathematics because when I did this computation, I got a positive number. And surely, when I wrote this over here, I'm saying that whichever direction they're moving is the positive direction. And even though he's moving a little bit slower because he threw the snowball, he's still moving in the positive direction. And then lastly, this one's a little bit tricky. And again, if I had the opportunity to rewrite it, I would probably change a few things. Let me just walk you through my own interpretation of what's happening here. I started off with we got a spaceship, and it's really far away from Earth, and we want to know how long it's going to take for them to get back if they fire their thruster in a certain way. And when a rocket ship or any spacecraft fires a thruster, they're basically expelling mass with a really high speed in the opposite direction that they want to go. So in the initial state, I basically said that the 56,000 kilograms that we have for the spacecraft, I basically made the assumption here that is the propellant P and the spacecraft itself added together. And so from here, I just decided that the spacecraft must be itself, without the propellant, must be a little bit less massive. And then the propellant, of course, has this much mass. So you might have made a different assumption here, maybe that the spacecraft itself has a mass of 56,000, and then additionally there's another 3,500 kilograms, and that's okay. It does change the result a little bit, and I could have been more clear in my explanation of this problem. But anyway, there's a couple more interesting things to notice over here where I write down all the things that I know and the thing that I'm looking for. I did decide that the propellant's velocity would be negative because that's away from the Earth. So I expect that my final spaceship velocity is going to be positive and that it's moving towards the Earth. And then finally, I have a distance and I'm looking for a time ultimately. There's really kind of two things we have to do here. First of all, we have to find the final velocity of the spacecraft after they expel the propellant. And then we have to use that to calculate the time it's going to take to cover this particular distance. And that's why over here I listed two formulas. Velocity equals distance over time, and the total momentum initially equals the total momentum final. And I'm going to start with this relationship. Initially they're at rest, so the initial momentum is 0. And that makes our lives pretty easily. We just have the final momentum of the spacecraft plus the final momentum of the propellant, and they must sum to 0. So again, I can rearrange this to solve for the thing that I don't know, and over here is everything that we do know. We get that negative sign when we subtract this term to the other side. And when I plug in all my numbers, I got the negative sign from my formula and the negative sign from my velocity, which cancel out, and I end up with 220 meters per second towards Earth. That's the speed of the spacecraft. And so now I go to this formula, I solve for t, and I introduce my subscripts here. That's the final velocity of the spacecraft. And when I divide that extremely long distance, which, by the way, just going back here, it was given to us in kilometers, and I converted it to meters. I was able to do that just by changing the exponent in my scientific notation. And when I do the division, I get like 30 million seconds. And that's an awful lot of seconds. And this is where my little clue over here comes in. It says, report your answer using the best unit. And what I mean by that is I want you to start thinking about our answers and what kind of sense they make. It's hard as humans to understand what 30 million of anything is, but in order to understand what 30 million seconds are, I just divided it by 60 to get minutes. I divided by another 60 to get hours, and then I divided by 24 to get days, and I got 350 days. So that makes a lot more sense to me than 30 million seconds. In other words, this spacecraft is going to take about a year to get back to Earth. And that's in terms that we kind of understand. So that's part 2 of this